Well, good morning, everyone. Welcome to another edition of Environmental Geosciences. I just wanted to take a moment at the beginning of the class here and apologize profusely for failing to recognize that the time for class had elapsed last time. It's quite embarrassing, and be sure not to let it happen again. I now have set an alarm so I can know when the class is supposed to end. I normally start moving around, and it sort of tips me off. Because that brings me to my second point that I have to say it's definitely not as much fun teaching without being able to see your faces and interact with you and make sure I know what's going on with the learning process. So with that being said, again, apologize for being late. I'm going to try to pick up today and hopefully get you out here a little bit early to make up for my tardiness in ending class last time. Where we're going to pick up again is with going through the age of the Earth, and I wanted to highlight the fact that although this background geology is very important, this section of the course is basically designed to get us through how the Earth came to be, what it is today that we look at. Most of what we're going to pick up with by the end of next week is actually getting into some of the environmental concerns related to the things that happen on Earth and perhaps a bit more societally relevant things. So if that's what you're excited about, hopefully you'll see that soon. Where I left off in the last class was really transitioning from the Proterozoic to the Phanerozoic, or these periods that include the Paleozoic, the Mesozoic, and the Cenozoic. And one of the things I wanted to get sort of discuss in a little bit more detail. I won't give this on your exam or anything like that. But I brought up the idea that when we have major mass extinctions for a variety of different reasons we can talk about throughout the semester, some being changing climate, runaway greenhouse gases, some can be meteorite impacts, some major episodes of volcanism, or even now potentially we consider things like pandemics. There are major periods throughout the history of the Earth where life as we know it is basically almost entirely wiped out. We call those mass extinctions. And one of the things about that in terms of the transition from the Proterozoic into the Phanerozoic, of which the first era is the Paleozoic, is the fact that we, basically the Earth as we think about it, the Earth that sort of we see today, really had a major transition from the Proterozoic, which included almost entirely simple life forms like prokaryotes and eukaryotes, to just the earliest onset of multicellular life at the age of this snowball Earth. So snowball Earth is sort of a major period where we have a runaway sort of cold Earth. Again, ice caps and glaciers probably down, encompassing most of the equatorial parts of the world. Certainly, even a lot of the global oceans would have been ice mass at that time. But that transition, that mass extinction, actually opened up an opportunity for diversity into the Proterozoic that allowed us around 540 million years ago, 542 to be exact, to transition into a period where life started to become more complex, multicellular, and actually lead to the transition to complex animals, plants, and really changed the way that life would be predominantly in the oceans to being on the continents. One of the things I want to highlight here, of course, is that this is also a period where the geology of the Earth is still evolving. Keep in mind that during this time, we're still seeing major episodes of continental accretion. And most of what we're going to talk about in the rock record from this time period of the Phanerozoic, including the Paleozoic, Cenozoic, and Paleozoic, Mesozoic, and Cenozoic eras, is actually a transition from a scenario where most of the plates were disparate, sea level was relatively high standing, and we start to see basically continental accretion, where we see more and more land masses crash into each other. That's called accretion, leading to what we start to see as the modern continents today. The thing I want to highlight here just briefly is, that I alluded to at the end of the last class, is that these transitions, both tied to geology and to changing climate here, are major opportunities after mass extinctions for a new radiation of life. And that's really what defines the beginning of the Paleozoic era, which is highlighted by the beginning of the Cambrian during this time, and the rock the rock record during this time, during the Cambrian, is called locally the Burgess Shale. It's some of the earliest forms of a major radiation of life around planet Earth. And it's also the formation during these major accretion events of what we call supercontinents, where all the land masses sort of got together. We saw a major landmass, and that provided a more opportune scenario for radiation of life, particularly transition to land. So on the topic of mass extinctions, what I wanted to bring up is this idea of this relation between mass extinctions and a renewal of life. Again, these are tied to geological factors, meteorite impacts, climate change. A lot of different things can lead to mass extinctions, and many of them are still areas of great discovery and great uncertainty for that matter. But basically, there's a tendency of the number of families here shown on the y-axis versus the age of the Earth before present. Here's present day. Here's 600 million years ago. So you can see during this time period, before we got into the Phanerozoic, you see very limited amount of, relative to today, number of species. And that's partly due to the fact that there were many fewer species on planet Earth. And also, it's hard to understand them as well because of the fact that the rock record is pretty limited beyond this time. After this first major sort of supercontinental formation of, again, called Pangaea, I won't test you on the name of that likely, but Pangaea is one of the first supercontinents we know much about. That's really the period where we start to see the Cambrian start with this radiation of life in the beginning of the Paleozoic. And notice what we see is that from there, for quite a long time, we see a major increase in the number of species on planet Earth. Basically, almost a 300-fold increase in the amount of life through Ordovician. And that was sort of following this mass extinction tied to the snowball Earth era. So before that, we think this number remains low, probably actually much lower than even on this graph. But most of that is also limited by poor understanding of the rock record. Okay. And what I highlight here with each of these black arrows is the fact that you have major episodes of mass extinction, and you'll notice that there are basically 5 major episodes of mass extinction tied to the late Ordovician, late Devonian, and then some which you might have heard about a bit more, sort of in the earlier parts of your science education, is the Permo-Triassic boundary. This is sort of the granddaddy of them all, if you will. This is the big one. This actually is the event that nearly wiped out entirely the life on Earth. Up to 95% of all marine species were wiped out during this time. Even a lot of single cellular organisms were wiped during this time. But notice that, again, after each of these mass extinctions, you see a re-radiation of life. And often, even though during this whole period we see the number of families stays about the same, what I want to highlight here is that there's a radiation of new biodiversity, different species during each one of these. So the Permo-Triassic boundary wiped out most of life on Earth. It was actually not very long after the radiation of life on the continents. But what you see after here is this is the end of the epoch of very simple life forms, things like trilobites and crinoids that dominated oceans. And this actually begins the era of dense vegetation on planet Earth, and also on some continents of Earth, I should say, and also the age of the dinosaurs, if you will. The one that you might have heard about, the end of the dinosaurs, the Cretaceous Tertiary, which now has been reclassified the Cretaceous Paleogene event. This is the period where the dinosaurs went extinct. And notice again, we saw a major diversification of life forms. So we went into more mammalian life, and actually led to the evolution that came to us having humans eventually on planet Earth. Not quite that time. This is a little bit hard to see, and I encourage you to sort of download this and look at this. I'll post it as an image on the files online as well. This gives you a sense of the tree of life, and basically looking back as far as we know, we had, again, simple eukaryotic life that had a diversity of species, eventually, or prokaryotes rather, eventually, simple bacteria. Eventually, those got outcompeted largely by eukaryotes. And notice there's this evolution towards various types of plants that gain more functionality in terms of just simple photosynthesis, red-green algae, and eventually this entire evolution up to about, around 500 million years ago, where you actually start to see more complex things like fish evolve in the oceans, amphibians, eventually reptiles in the age of dinosaurs, and birds. And notice that how many, I think it's useful to think about how many variations of species led to the actual evolution of what we see on planet Earth today. So there are some things like crinoids and trilobites that live for extended periods of time, but in reality, we sort of have an ecosystem. We often see that major mass extinction events. So some species are no longer competitive for even for biological reasons rather than big catastrophic reasons. And as a result, you see that those mass extinctions lead to often radiation of biodiversity. One of the things I wanted to highlight, will be a theme of our course as we go on, of course, is the fact that most scientists accept now that today, modern, we actually would call this the Anthropocene. Or anthropogenic means related to human interactions. And most people accept that we're actually in a major mass extinction event today, that there is a rapid decrease in species, and that doesn't bode well for, of course, the long-term sustainability of our various ecosystems. But key thing I want to remember here is that, the combination of coming out of the snowball where we actually have a rock record we can look at and understand what's going on, and the fact that we saw major mass extinctions allowing for radiation of life. We saw basically an age of fish, an age of land plant radiation, major mass extinction, and then basically age of the reptiles, birds, and then eventually mammals, all during this process. And I'm speaking of those generally, and that's okay for the purpose of our class. We don't need to get too detailed into them. But just show here for an example from a field trip I took students on for a different class. This clay layer here is actually the age of the Cretaceous Paleogene, or previously called the Cretaceous Tertiary boundary. So if you look in here, you can actually find dinosaur fossils. This is in Colorado. You actually find dinosaur fossils in this formation. You find this clay layer that it's basically a major extinction, and then above that, the next time you start to see fossils, eventually is irradiation of birds, and eventually up the rock record, you start to see mammals. So you really can actually go out to the rock record and see these differences in fossils we're talking about. So the Paleozoic, again, largely defined by new radiation of life starting in the Cambrian and the Ordovician. This is largely going to be small, relatively simplistic, but multicellular, cellular life, and some small sort of ocean fish, trilobites, crinoids, things like that. This period in the Devonian is also tied to the massive radiation, really the Silurian and the Devonian, all part of the Paleozoic, massive radiation of land plants. And for those of you thinking about natural resources, the two major oil and gas reservoirs or source rocks in Ohio and the Appalachian Basin both were deposited during these massive radiations of life at the beginning of the Cambrian, and also going back here at the late Devonian event. That radiation of life beyond that actually also led to another major oil and gas deposit in the region. So the next era is the Mesozoic. Meso meaning sort of middle, and it begins with just like I just described in various mass extinctions, it begins at the end of something else, and really the end of the Permo-Triassic boundary, or the Permo-Triassic event creates the boundary for the end of the Paleozoic and the transition into the Mesozoic. So again, the Permo-Triassic wiped out 95% of species, almost, as far as we know, almost 100% of the land species during that time. At the end of the Mesozoic is defined by the age of the Cretaceous Paleogene event, where the dinosaurs were wiped out. So the Mesozoic is sort of near and dear to our hearts, as certainly as young children. My two young children love dinosaurs and love hearing about that time of major radiation of land animals, massive animals with often big dense trees. But the other thing about this period is it's typically defined as a very hot time on Earth, high CO2 concentrations, hot Earth, and often was a scenario where the vegetation on the land was often characterized by much larger, trees and vegetation we'd expect today, and largely serving why the dinosaurs were so successful during that time. For those of you who haven't really learned about this before, does anyone know what caused the Permo-Triassic extinction? I might have already alluded to that, but there are a variety of different theories. Some suggest it's asteroid impact. Some suggest it's a rapid instance of volcanism, and others have suggested that actually it's neither of those. It's related to massive methane releases from geological formations that cause the CO2 levels in the atmosphere to increase and eventually cause mass extinctions. But I think today the most accepted is the fact that all of these factors seem to play a role. There is clear evidence in an area near the Yucatan Peninsula, Chicxulub, Mexico, where there's a large bolide impact that's almost exactly contemporaneous with the age of the final part of the dinosaurs' extinction. But most scientists today recognize that there's a bit more nuance to this. I apologize for going back and forth, but that actually all these events, as you see here, but including the Cretaceous Paleogene extinction of dinosaurs, that there's a trend where life is slowly dying off, and often it's more that these major events, such as the impacts of impacts of meteorites, sort of are the final straw, rather than the entire reason the event collapsed, which is philosophically interesting to think about in light of the fact that we live on planet Earth with a rapidly declining number of species. So, the key event here is that most people think the key trigger that finalized the age of the dinosaurs ending was an asteroid impact in Chicxulub, Mexico. But certainly major episodes of volcanism, the separation of these massive supercontinents led to erosion of different rocks and release methane. All these probably contributed, but based upon what I suggested earlier, the key things I want to highlight here is that in all instances, independent of the PT boundary or the PT boundary or the Cretaceous Tertiary or Cretaceous Paleogene boundary, some life survived, and actually in reality, life started to thrive. So the major transition, we're getting closer to our time here, to mammalian time, is really around around 66 million years ago. As mammals started to creep in during the small mammals, so think of things like small rodents and things like that, started to creep in during the Cenozoic or the Mesozoic. But the Cenozoic, again, starts in about 66 million years ago. It's tied to the end of the age of the dinosaurs. And really, it's the point where the life that survived typically and began to thrive, filled the niche left by the absence of the dinosaurs, was mammals, birds, and for some amount of reptiles have survived, of course. In fact, birds are, in many cases, tightly genetically related to pre-existing dinosaurs, as are things like snakes and other reptiles like that. So the mammals and birds that survived the Cretaceous Paleogene extinction went through a pretty rapid radiation into their modern forms, and that's really where the last 66 million years, relatively young geologically, if you will, led to a scenario where we see a large amount of the radiation of life. So one of the key things I want to highlight here is this immense disparity in timeline, right? If you look back here at this graph, we almost have no rock record that remains beyond about 600 million years ago. 600 million years is about one eighth or whatever of the total history of Earth. So the key thing here is I want to set a mindset in this class is that we have to recognize that the timeline of Earth is actually quite long, and the history of what we can know about geology is actually quite short by comparison. So if you do a 24-hour timeline, you can play this game in a variety of different ways, and probably you already have in other courses. But if you want to think about this as a 24-hour day, the Earth starts again in that sort of solar nebula where those individual dust particles get close enough to gravitationally attract to each other. As more and more bigger particles basically become attracted to each other, you see sort of space debris start to form, all the way to the point of sort of protoplanetary solar nebulas. Our solar system probably gets more than 99.9% of the mass into the sun, and gravitational concentration of those particles that start to aggregate lead to protoplanets and eventually planets like Earth today. Okay, so this is all at time zero. Remember, within about the first 200 million years, so before we even get to maybe, before we even get to hour number one, fairly early on, we see the Earth go through a lot of interplanetary violence, a lot of volcanism, a lot of degassing of the materials and heat by radiation produced in the Earth or trapped by that process. Fairly early on, within the first hour, we start to experience interplanetary violence and bombardment or late bombardment of things like comets and meteorites that bring the key elements for life, water, along with us having some landform to accumulate that water, so the protocontinents, and in fact start to develop an atmosphere. And really, relatively speaking, early on, by about 4 a.m., life starts to begin. But the key thing I want to highlight here is that life is really a lot of fits and starts of very primitive single cellular prokaryotes by 4 o'clock, and a much longer period of time before we actually start seeing things like eukaryotic life evolving and complex life forms. And really, for perspective, by the time you get to something as simple and as sea plants and jellyfish, you're already at 9 o'clock at night, right? So these are the first evolution of more complex life forms beyond sort of things like bacteria, algae, and funguses. You're already at 9 p.m. and by the time we get to this period of more complex life forms such as trilobites, other organisms. And I keep saying trilobite, and I recognize that I didn't put a picture of one of these on here, but that's actually one of the more common fossils found in Ohio, which I'll post a picture of online. But you're actually after 9 o'clock by the time by the time that the earliest stages of more complex multicellular, but still very simple mammals, or sorry, simple animals start to form. And that's part of the Cambrian explosion. And most of the geology you would ever observe in Ohio or the Midwest in general is all going to be Cambrian or younger. So that's tied to the Phanerozoic period, so after the Proterozoic. And if you live, and for those of you who might live over in Cincinnati or spend some time in that region, the Cincinnati Arch is a geological formation where there's a sort of a stratigraphic units that come up and have a topographical high around the area of Cincinnati that extends all the way up to into Michigan, actually, is a topographical high. And that area is actually one of the few places where the older rocks are exposed at the surface, and you can actually see, the older rocks at the bottom of the stratigraphic sequence, where you can actually find Cambrian rocks. And as a result, there and some of the areas up from Cincinnati to sort of Richmond, Indiana, that whole topographical high is a pretty famous, globally famous fossil site where people come from all over and actually pick out very carefully trilobites and other organisms to understand this first radiation of complex life, right here in Ohio. But it was all the way, to almost 10 o'clock, if you want to go stick with this 24-hour timeline, until you see plants start to actually radiate and colonize onto land. That's a very important aspect for Ohio, obviously, at least historically for Ohio. That major episode of continental plant radiation starts in something called the Silurian, so about 400 million years ago, but really got going by the Pennsylvanian Mississippian ages, sort of at the about 350 million years ago on, and it's in fact relevant to the life, relevant to the history of Ohio in particular. This plant colonization, when this really got going by what's called the Pennsylvanian and Mississippian age rocks. You see major coal deposits that were mined for more than a century here in eastern Ohio, Kentucky, West Virginia, Pennsylvania, etc. So but that's all relatively late in the game. Now, the key concept I want to highlight here is that the complex life forms we tend to understand as planet Earth today, basically started, stopped based upon evolutionary selection, and also were catastrophically stopped based upon major mass extinctions and subsequent episodes of rapid biodiversification and massive radiation of life forms. That's all relatively late in the day, if you will, relatively recent. And it was only right around 10 o'clock that you find that animals start to colonize land. Before this, it was relatively simple animals like trilobites and small things we think about as sort of shell-based fossils, stuff like that. And then, for perspective, by the time we actually see the Earth covered by the great forests that and great radiation of life that we see today, you're looking at a scenario where you're almost getting to 1030. The dinosaurs, which we tend to think about as prehistoric dinosaurs, obviously they are prehistoric by a great number of years. But to give you perspective on time, it's almost 11 o'clock when the dinosaurs even arrive, let alone the fact that the age of the dinosaurs goes on and the dinosaurs are lost. So, by about 11:38, getting close to 22 minutes from midnight, the dinosaurs are extinct, and really that's what kicks off the age of the mammals. Now, clearly here we're not talking about these mammals being humans. In fact, I'll ask a quick question here. Does anyone actually know how long ago that humans are thought to have started to evolve from into what we see as Homo sapiens today? Since no one's feeling likely to respond on a Friday morning, I understand that. I'll give you a sense of this. Okay, so I got a guess of about 100,000 years ago. Some say a couple hundred thousand years ago. That's not a terrible guess. In fact, a couple 100,000 years ago sounds like a really long time, and in fact it is. Geologically, of course, it's almost instantaneous. But the earliest estimates, there's a famous fossil site in Hadar, Ethiopia. where they have very accurate age dating of the rock units above and below hominid fossil. And the estimates in that I think are more likely more in the time frame of 1.5 million to 2 million years ago, where it's still a lot of debate as in terms of what's the exact differentiation between our ancestors, genetic ancestors, and Homo sapiens. But it's probably more along the lines of something we probably wouldn't recognize as exactly like us, but transitions towards hominids about 1 to 2 million years ago. But for perspective, most of the radiation of populations out of the great cradles of civilization, like the Rift Valleys in Africa and the Yellow River and the Tigris and Euphrates, are certainly much more prevalent as we go on. A similar idea to that really rapid expansion over time. So clearly, the last few 100,000 years have been the age where humans have started to play a role in this. But for perspective, in terms of the age of the Earth, that's actually at 11:58 and 43 seconds with the fact that humans actually even appear. It gives you a perspective. We're certainly not the first tenant of planet Earth. We're actually really just the latest in the game, and probably there's going to be some species that exist long after we're gone, and we just see what they become. But thinking about it sort of more holistically, what we know about these last few million years is that there have been geologically a lot of factors that led to us getting here, right? For starters, one of the things relevant to this class, when we think about things like climate and water and food, is that you've seen this is a major period from the age of the end of the dinosaurs. We see the carbon dioxide levels on planet Earth decreasing steadily, right? We see the vegetation being more attuned to there being mammalian life evolving, and there's a lot of geological factors that we'll talk about more as the semester goes on. Don't worry if you're not picking up the details now. I'm just trying to get a general sense of a general perspective of where we're going to go. Is that most of the mammalian evolution, and certainly all of human evolutions, occurred at periods where the Earth is actually in some of the lowest carbon dioxide times in its history. For perspective, that is, although I referenced snowball Earth, well before 600 million years ago in the last lecture, we're certainly nowhere near that. We're actually also evolving in relatively cold times, where warm-blooded life forms are more adaptable to survive. And most of what happens in the evolution of humans from about minute and 17 seconds before midnight and midnight is actually dictated by things like relatively minor episodes of climate change, like handling things like the episodic cycles of about 100,000 years between glacial and interglacial periods, which are all dictated by relatively small, I wouldn't call them microscopic trends, but certainly not mega trends in climate change, like 100 million years or 65 million years of declining CO2 concentrations. But actually, it's mostly us adapting to glacial periods and interglacial periods that have about a 20,000 to 100,000 year minor cycles that dictate where humans are going and all that we've evolved in. So most of the understanding of the early appearance of humans is tied to near equatorial warm environments. Certainly, most of the data we have on early human early human migrations have been tied to the last about 40,000 to 100,000 years. But for perspective, while we know of certain early cradles of civilization in near equatorial areas in Africa and the Middle East and Asia, Southern Asia, we probably, for perspective, don't see the earliest Native Americans making their way to places like North and South America till within the time frame of about 100,000 to 40,000 years ago. Even during that time, we've had major mass extinctions, if you will, on a human scale, just in terms of response to climate changes. For example, one of the most famous occurs, geologically instantaneously close to midnight about 12,000 years ago, but long on our human timescales, where there's an event called the last ice age, and particularly something called the Younger Dryas event, where you're coming out of an ice age. Humans started to radiate, about 40,000 years ago, and then the onset of another ice age called the Younger Dryas about 12,900 years ago caused another massive freezing, and there was a major loss of life and human population, I should say, in North and South America, and also gives you a perspective. That's the age that wiped out the things like the woolly mammoths in North America, which you can find fossils of quite near to here. but it's also where things like the saber-toothed cat and other species in North America were sort of wiped out by these smaller scale climate events. The point I'm trying to make here is that although I spent some time introducing the idea of mass extinctions and these cycles, I guess the point I'm trying to make here is that on top of those macroscopic scales that wipe out massive percentages of the species on planet Earth, there are always this continuous balance between the Earth's wobble and the solar radiation and sort of the elliptical orbit of our transport around the sun and within the solar system that cause minor climatic variations that we're only just being able to tease out in the rock record based in more recent times. We're looking at things like ice cores and marine sediment, stuff like that. And what we do know is that from a big picture perspective, I'm not trying to scare you directly, but is the fact that on a macroscopic on a mega trend or a macroscopic trend, we are seeing a major decrease in the number of species on planet Earth today. But on the background of that is always this continuous cycles where, in light of climate, access to resources, changing climates and changing things like water access, of course, also lead to local devastation of species and populations. So the key point I would like to make here again is just providing this perspective that all of recorded history, the earliest recorded history of stories and cave paintings, things like that, still is no longer than about a second or a second and a half on the history of Earth. So it's hard to actually conceive of that. The psychological research suggests that the human brain's not really capable of understanding what 1,000 of something really is, and certainly has almost no capacity to understand what more than 1,000 of something really is. But one of the things we're going to have to think about here is, and it's relevant to sustainability and thinking about our systems in a major way. And of course, population growth, our three themes get tied back to this, but it's the fact that we are going to try to spend most of the semester talking about, key elements of the environment that lead to us trying to create a sustainable, system for us to live in and how to adapt to planet Earth. But we're going to try to think about human lives that are, 75 years on average in places like the United States, much lower in other parts of in other less developed countries. And we're going to try to juxtapose those with geological processes that happen on millions of years, where in fact the history of humanity, is about a second of a 24-hour day for perspective. So John McPhee, he wrote a famous book about his travels across the United States. He's a geologist, and here's just a picture from the book. In the Basin Range, John McPhee explains that the distance from the fingertips of one hand to the wrist of the other is just till we get to the Precambrian, right? So or just till we get to the end of the Precambrian. That basically gives you perspective that from here all the way over to here is basically the part of the Earth's evolution where we actually didn't see any radiation of complex life at all. All the complex life, and that's going back to very simple mollusk-looking kind of shellfish, very small things. All the complex life is within the case of one hand. And in his book, he says, in a single stroke with a medium-grain nail file, you will eradicate the entire, human history entirely. So just to give you perspective here, I know I'm just saying the same thing in different ways now, but what we're going to need to think about is how do we recognize our place on planet Earth? How do we build sustainable systems in light of the fact that these, sort of macroscopic processes have been in process for billions of years? And it's a challenge to really think about that. And I'm not expecting you to get it from just this discussion alone, but it's worthwhile to recognize that most of the events we're dealing with in humanity are trying to adapt rapidly to something that's gonna change on a day-to-day basis. But in reality, the processes like earthquakes, volcanoes, climate change, not that we can't do a lot about preventing anthropogenic-derived climate change, but macroscopic, reorganization of plates that change the background on which our climate is based upon, are processes that are in line and ongoing for billions of years. And where we're going to go after this lecture is basically another round of lectures on just the structure of the Earth and how it sort of comes together. And after that, we'll get into more about the sustainability and the live there systems that are tied to those processes. So just to recap, I'm going to try to get you out of here a bit early today, since I took up about an extra nearly 15 minutes last time. The Earth is about 4.5 billion years old. 4.55, 4.56 billion years old is our estimate. Key thing is that and these are key points, meaning I want to highlight them on. They'll be highlighted in upcoming worksheets and exams if they weren't already in this one. Radio dating techniques were used to determine the value of the Earth. Clearly, those radio dating techniques have a lot of different applications today, but the ones we're talking about are largely using uranium-lead series radio dating techniques of meteorites to determine the age of the Earth. And the key challenge in sort of getting a more accurate estimate, again, is the fact that most of the rocks we find on planet Earth have been reworked by plate tectonics to the point where they're not actually able to be age dated. So for perspective, what we know is that the age of the Earth is about 4.55 to 56 billion years old. And by about 4.3 billion years old, we got to the scenario where we actually had protocontinents and enough water and geological processes started sufficiently to create sedimentary and later metamorphic rocks. So that gives you a sense of an incredibly dynamic planet for about nominally 200 million years that led to the scenario where we started to get the processes we think about as Earth and plate tectonics and even life getting going relatively rapidly. So the age of the Earth allows us to consider things like processes related to plate tectonics, evolution, and gives you a sense that a small perturbation in life in the ecosystems on planet Earth, and we sort of a growing recognition that can have major implications. But just think about the fact that life had evolved over billions of years. So changing things like habitats, changing things like eradication of species, that can cause pretty long processes to recreate sort of ecological sustainability in those scenarios, because plate tectonics, other geological related processes, and evolution of life happen really, really long. So, key point here again is it's simple life form relatively quickly. That's the sort of interesting thing to think about, and especially thinking about exoplanets and the rest of our solar system, outside of our solar system, is the fact that, from a statistical perspective, many scientists believe that because of the fact that simplistic life forms, eukaryotes, prokaryotes being first, developed relatively quickly on Earth, and actually fairly early on developed things like photosynthesis that oxygenated the atmosphere. One of the things that we tend to talk about a lot in in elementary school and college and high school about planet Earth is the fact that we have water, and that's what makes us unique. And clearly, water is the key component for life. But one of the things that's where most of the NASA and other exobiology research think about is the fact that, based on the fact that a simple life can be developed and rapidly evolve, that looking for evidence of photosynthesis, i.e. looking for evidence of oxygen in the atmospheres of planets, is actually a way to get an understanding of whether life has evolved in other locations. And that can be done with spectroscopic needs, looking at the light that comes back from different components of this. So, just like the story of humans being, almost instantaneous on a geological timescale, more complex life has only appeared relatively recently. For perspective, the Phanerozoic, if you were to be alive in a Phanerozoic world, you would think of everything as clearly prehistoric vegetation and small, simple animals in the oceans. But that's actually, only 540 million years ago. But compared to the history of the Earth, it's still relatively soon. And then clearly, humans have only been around, almost instantaneously, and it's quite interesting and in some ways saddening to think about how much we've impacted planet Earth in such a short period of time. And one of the key things I want to highlight here is just thinking about the fact that our irradiation of immense population growth since the last 80 years in particular, how much potential we have to change it in a much greater way than we have already. So that's going to end the actual lecture part of the class. I think I've hopefully given you your 15 minutes back that I stole from you on Wednesday. Again, I apologize profusely for that. As a reminder, the worksheet's already online. It's due by midnight tonight. Shouldn't be. It seems like everyone's making really good progress with that. Hopefully those aren't problems going on. The lecture for next week will be posted on the files under lectures. This video recording will be on the modules, and the new lectures and worksheets we posted on Sunday night for next week. There's no class Monday because of the fact we have the Labor Day holiday. So everyone will get a long week and long weekend rather, and I'll look forward to talking to you all on Wednesday. Thank you very much, and have a great weekend. If anyone has any questions, I'll hang around for a few minutes.